All right, good morning. Let's get started. So, in today's lecture, we're going to look at evaluation of truncation error for unsteady diffusion. Okay. So, this is unsteady diffusion. Evaluation of truncation error. Okay. So, what are the assumptions we have made in the unsteady diffusion equation? Well, okay. So, there is no convection term, that is why we got the unsteady diffusion equation. In terms of how did we approximate some of the things, for example, in the steady diffusion equation, we had the source term was evaluated as the cell centroid value, right. Likewise, we have made several assumptions in the unsteady diffusion equation. What are those? So, if you look at the unsteady term, we had this rho phi p 1, right, and rho phi p 0, right. These corresponds to the t plus delta t and t values, right. These values, what did we say? We said that these are representative of the cell centroid values, right. Phi p is what we have used, right. So, these are again represented by the cell centroid values. And then if you move on to the other terms, we had the same spatial approximations, right. For example, the source term that we will have, we will again say that this would be represented by the again the cell centroid value and the phase fluxes, that is gamma grad phi on the phases are represented using the phase centroid values, right. Okay, and what else? What other assumptions we have made? Linear profile assumption for the diffusion fluxes as well as the source terms between T0 or T and T plus delta T, right. That is what we have made. That means, and we said depending on the type of the scheme, either T0 values prevail over the entire delta T or T plus delta T values prevail over the entire time step. That is what we said. So, that means the source terms S bar and gamma grad phi f, let us say if we are talking about an implicit scheme, this is a fully implicit scheme, then the values at T plus delta T prevail over the entire time step, right. That is what we have said, right. Anything else? We have any other approximations we have made in discretizing the equation? That is all, right. We had an unsteady term and the diffusion and the source terms, right. So, both of them we said either it will prevail t values or the t plus delta t values prevail over the entire time step, and if you consider an implicit scheme, it is the T1 values, right. Okay. So, then let us evaluate each of these approximations. So, what is the first approximation? Rho phi p1 and rho phi p0, these are represented by the cell centered values. So, what will be the order of accuracy for these terms? This is basically a mean value approximation, right. So, we have already seen that this would lead to a mean value approximation lead to what? Second order in space or time? Space, right. This will lead to second order in space because phi p is what we are looking at, right. So, this is order delta x square in space. What about the second assumption, S bar and gamma grad phi? This is also mean value approximation, right. We are calculating the integral S dV with S bar times delta V, right. So, this is basically integral S dV is represented as S bar times delta V, saying that this is the centroid value. This is also, both these assumptions lead to a spatial order of accuracy of what? Which order? Second order. Okay. What is the third one? Third one is about time, right. So, this is basically talks about if we have a source term or if we have the diffusion fluxes, these are will kind of incur some temporal order of accuracy, there will be some temporal error, that is what we have to evaluate. Okay. So, that is what we are going to see next. That means, let us say if we consider a source term, that is S dV dt. Okay. So, this is already let us say some S bar, that is on the volume, S bar dt integral from t to t plus delta t, right. This is what we have to evaluate upon delta t would give us some kind of an average value, right, for the S bar over the entire time step. Okay. So, let me consider first a source term, that is S, which is expanded about S at t plus delta t. Okay. So, we have now S0 and S1, which represent t and t plus delta t values. Okay. We are interested to calculate what is integral S dt over the range of delta t, right. So, then let me, because I am considering an implicit scheme, let me expand S about S1. Okay. So, that is we are expanding S, that is at any time instant t, about S1, that is at t plus delta t. Okay. Or basically we have S0 and S1. Okay. Fine, then if I use Taylor series expansion, what would be S? S would be, if I were to expand about S1, okay, let me call it as this is basically S1 plus partial S partial t of 1, right, times t minus t1, is that correct? Just like what we have done for the spatial expansion, I am expanding about S1 in time, right. Yes, question. Not S0, I have S at any time level t. Okay. So, I have here basically T0 and T1 and T that is intermediate between these two. Okay. So, S0 corresponds to T0, S1 corresponds to T1 and S corresponds to any time t. Okay. Now, we are interested in calculating what is the integral of S dt over the range t to t plus delta t, or I can write this as T0 to T1. Okay. That is what we are interested in. T1 minus T0 would be over delta t, right. T values are at any time, T1 is the final value after the delta t, T0 is the previous value between the time steps.
So, in the second term, will it be T1?
This one? You mean this guy?
Yeah.
So, essentially you have let us say if you go back to the spatial expansion, we had some x, right, and then we had expanded about xp, right. Similarly, I have some time t which I am expanding about t1, right, or t sub 1, right. Basically, that corresponds to the next time step, t plus delta t, right, next time. Yes. Essentially, it is partial s partial t evaluated at 1, right. That is not dou s 1 by dou t. It is essentially everything is evaluated at time level 1. So, that carries a timestamp of that, okay, of 1. Other questions? Should this be minus or plus? Plus, right? Okay, fine. Any other questions? No? Okay, then shall we complete this? So, what will be the next term? Partial s square by partial t square evaluated at 1 times t minus t1 square by 2 factorial and so on, right. We will have the third order terms and so on. Okay. Now, of course, what we are interested in is basically integration of s over the time step, that is going from t0 to t1 is what we are interested in. So, let us calculate this. So, basically integrate on both sides of this equation over the time step t0 to t1. Okay. So, this will be integral t0 to t1 s1 dt plus integral t0 to t1 partial s partial t1 times t minus t1 plus integral t0 to t1, I would write it down here, plus integral t0 to t1 partial square s by partial t square, evaluate 1 t minus t 1 whole square by 2 factorial dt, and there will be a dt here, okay, and so on. Fine. So, whatever the Taylor series expansion we have here, okay, we have integrated over the time step, right. This is essentially what we have in the unsteady diffusion equation, right. We have approximated this using S1, right, S1 times delta t, that is what we have approximated, or S0 times delta t if it were an explicit scheme. Questions? Yes. First term, which one? Which first term? You mean this equation? This equation? The one above here? This should be T1 minus T. Why it should be T1 minus T? So, we have time step T, that is between T0 and T1, and we are expanding about T1, right. Right. So, this is basically T minus T1, right. So, T1 is the values at 1 are known, or we are actually expanding about the next time level values. Okay. So, this is kind of a forward values we are using. Fine. Other questions? No? Okay, this is good. Then what will be the values of S1 and partial S partial T1? What about these values? These are all constants, right. So, can we integrate this equation on the right hand side and tell me what would be the right hand side? So, this would be S1 times integral dt would be how much? T, T1 minus T0 would be delta t, and then plus partial S partial T1 times what would be T minus T1 dt. Again we have to use some other variable, some p or something, right, and change of variables, right. So, if I use a change of variables, what will be the limits? Minus delta t to 0, and this would be some p dp, right. If I use some other variable, this would be okay, plus and so on. We will have some more terms here. Okay. Now, what will be the integration here? So, this will be S1 times delta t plus partial S partial t 1 times what would be this value? Integral p dp would be p square by 2, right. That would be delta t square by 2 with a plus or minus? Minus. So, this will be a minus delta t square by 2 plus something. Okay. Fine. So, essentially if you go back, what we are interested in actually is an average value, right. That is nothing but integral T0 to T1 S dt upon delta t, right. That would be the average value. That is what we are interested in the equation that we have already derived. So, what would this lead to? So, essentially we are dividing the entire equation with delta t, right. This would leave us with S1 minus delta t by 2 times partial S partial t 1 plus and so on. Is that correct? Yes. This is the lower limit. So, you will get a minus. There is a square. So, upper limit is 0 minus lower limit has a square. This will lead to minus delta t square by 2, is not it? Correct or no? Correct. Essentially you get a p square by 2 going from minus delta t to 0, right. So, this will be 0 minus, you will get minus delta t square, it will be a minus. Okay. Fine. Okay. So, this is what we have. Now, what is on the left hand side? Left hand side is what we have used in the equation, right. This is what we have used in the implicit scheme, right. We have replaced this term with what? S times S of 1 times delta t, or it would be this value would be S1 is what we have used, right. We said the source term and the diffusion fluxes are assumed to be the t plus delta t values over the entire time step. That is what we have used. So, that is what we said, we approximated integral t0 to t1 s delta t dt, right, this guy with s1 times delta t, that is what we have used. And what is the error we are committing in doing so? Whatever is left over is what we are committing as an error, right. Now, what is the order of accuracy of this error? First order. So, this will be only order delta t. Okay. So, this implicit scheme that we are working with is only first order in time, and all other spatial assumptions are second order in space if we have a uniform mesh. Okay. So, the implicit scheme is first order accurate in time, and if you have a uniform mesh, then this is second order accurate in space. Okay. Fine. Now, of course, we are not going to derive the order of accuracy for the other two schemes, which are basically the explicit scheme and the Crank-Nicolson scheme, okay, which is what you will do and verify them later. Okay. So, without proof, we are stating here that the explicit scheme would turn out to be also order delta t, okay, and the Crank-Nicolson scheme would turn out to be what? Order delta t square. Okay. So, this is what I am not proving, but you have to verify these. Okay. Now, how would you go about calculating the temporal error for explicit scheme? What is that you would change in the beginning? You will expand about S0 and so on. Okay. What about Crank-Nicolson scheme? Where would you expand about? S half. Okay. So, that is what you have to kind of try and see whether you are getting the delta t square for the Crank-Nicolson scheme or not. Okay. So, that is for you to verify. Questions on this till now? No questions? Clear? Okay. So, now we have established the truncation errors both for space and time for the steady diffusion as well as for the unsteady diffusion equations. Okay. All right. So, we have one more topic that is left over, which is basically the stability analysis, right. We said in looking at these temporal equations, right, these temporal schemes, we said the explicit scheme is only conditionally stable, whereas we also stated that the implicit scheme and the Crank-Nicolson are unconditionally stable, right. We have said this, but we have never proved them through any analysis, but for explicit schemes we have used something like something known as a heuristic method, right, where we said if the coefficients of phi p0 let us say have to be positive, then you ended up getting a condition, right. That is what we have done, which is a heuristic method. So, now we are going to look at a proper analysis that is known as Von-Neumann stability analysis. So, we are looking at stability of the time stepping schemes. Okay. So, we will use one method known as the Von-Neumann stability analysis. So, this is a classic method that can be used to check the stability of the time stepping schemes we have. Okay. So, this can be applied for if you have simple 1D problems with zero source term and without any nonlinearities and things like that. Okay. So, that is what we are going to do. So, essentially what this tells us through this stability analysis is if we have a time stepping scheme, are the time steps that we are choosing going to keep the round of error stable or not. Okay. That is what the stability analysis tells you. So, essentially if we have a particular time stepping scheme, do the or does the time stepping keep the round off errors from growing from iteration to iteration or from time step to time step. Okay. So, here we have to kind of pay attention to this word, which is basically the round off errors. What are these round off errors? Why do we get round off errors, or where do we get them? Computationally, essentially numerically, right. If you want to, so truncation error is different from the round off error, right. Up till now we have looked at truncation error, which is order delta t, order delta t square, delta x square and so on. What is round off error? Round off error is basically the inability to represent a floating point number exactly in a system, right, in a computer. So, essentially we have round off errors, right, does not matter whatever is the accuracy you use, you still have round off errors. Now, that is what we are using to kind of base the entire analysis on. Okay. So, these round off errors, if they are bounded, if they do not grow from time step to time step, then we end up calling the scheme as a stable scheme. If the round off errors grow from time step to time step, then we call it as an unstable scheme, which will eventually lead to the solution diverging. Okay. So, the entire analysis is based on existence of round off errors in the computer. Okay. So, that is what we will do. So, the error we encounter at any time step is the round off error is what we would call in the stability analysis. Fine. So, again the stability analysis can be performed for each of the three schemes that we have looked at, which is the explicit, implicit and the Crank-Nicolson. Okay. For the purpose of the demonstration, I am going to use only the explicit scheme, okay, and see if we can come up with a stability analysis for this particular scheme. Okay. If we can come up with the condition that we have already realized in the previous lectures. Okay. So, let us look at the explicit scheme, and if you go back to your notes and see what would be the discretized equation for the explicit scheme for an unsteady diffusion equation. So, that is basically A p phi p equals sigma A and B phi and B 0 plus A p 0 minus sigma A and B times phi p 0 plus some B, right. That is what we have here. Phi p without any superscripts indicates the current time level values at time level 1, right, or t plus delta t, and phi p or phi and B 0, they all indicate values at time level t, right. That is what we have. Now, for the sake of simplicity, let me assume we are looking at a one dimensional problem, okay, and the source term is also 0, and I will also assume that the diffusion coefficient gamma is a constant. Okay. This will make our life simple in the analysis. So, I am assuming a 1D problem with no source term and gamma equals constant. Okay. So, 1D problem meaning the area is also 1, right. So, essentially the unit area vectors for the cells. Okay. So, you do not get the delta y or a for the east and west, they are all ones. Okay. So, if the source term is 0, which terms in this equation go to 0? B is completely composed of SC and SP. So, this would be 0, this term will not be there, and what would be the neighbors? If you are looking at a 1D problem, what are the neighbors? Only east and west, nothing else. Okay. Fine. So, let me write down the corresponding equation, kind of a simplified equation. That would be A p phi p equals A east phi east 0 plus A west phi west 0 minus, or sorry, plus A p 0 minus A east minus A west times phi p 0, right. That is all we get for a 1D no source constant gamma. Okay. Now, what is A east? What will be the expression for A east? Gamma delta y is 1 upon del x e. So, because it is uniform, I would represent it with using gamma by delta x. Okay. We are using a uniform mesh as well. So, that is another assumption. We are looking at a uniform mesh. Fine. Then what will be the value of A west? same as this, right, because it is uniform, and it will also, this will also equal to A west. What will be the value of AP 0? Rho delta V by delta T. So, for the context of 1D, what will this be? Rho delta X upon delta T. And what will be the value of AP for an explicit scheme? What will be the value of AP? Can you go back and see? AP would be equal to AP 0 for explicit scheme, isn't it? Right? For explicit it is the same. For implicit you will have extra terms. So, this will be same as AP. AP equals AP naught for an explicit scheme, right? We have derived this before. Okay. So far so good. So, we have now made several assumptions and got these equations. Now, what I would say is that let us say we have an access to a an infinite precision computer. Okay. So, we have some computer which has infinite precision, right. So, that means the solution you would get out of that computer would have 0 round off errors, right. So, we have an access to infinite precision computer. Okay. That means it would give you 0 round off error. Okay. As a result, the solution you would get from this infinite precision computer, we would like to denote it using some capital phi. Okay. Whereas, what we would get from this above equation, we would call it as, let us say 1, that is basically solution coming out of a finite precision computer like what we have with us, right. Okay. And the second one which we are talking about is an infinite precision computer whose solution will be capital phi. But what equation do we solve on this computer? Same discretized equation, right. Only thing is that the solution little phi p and the capital phi p would differ by what? By the round off error at that cell centroid, right. That is the only difference. Okay. That means or the accumulated round off errors at that cell centroid. Okay. That means the solution capital phi p on a infinite precision computer would come out of solving this equation. AP phi p equals A east phi east 0 plus A west phi west 0 plus AP 0 minus A east minus A west times phi p 0. Okay. Fine. So, this is basically a solution that is coming out of 0 round of error calculation. Okay. And now, we would like to call the difference in solution between phi and this capital phi as the what? As the round of error. Okay. That is basically all the accumulated round of errors coming into play. Okay. That means I can calculate what is my little phi from here as epsilon times capital phi, right. The solution I have is basically add the round off error to the exact solution, and that is what my actual solution that I got. Okay. Now, can I substitute this little phi back into equation 1, right. Essentially take this guy and substitute into equation 1. Can I do that? Right. Essentially we have now little phi which is the actual solution. So, we will plug it in here. So, what will that be? That will be AP times epsilon p plus capital phi p. These are all evaluated at 1 equals A east times epsilon E 0 phi E 0 plus A west times epsilon west 0 plus phi west 0 plus AP 0 minus A east minus A west times epsilon p 0 plus phi p 0, right. We got another equation which is in terms of epsilon and capital phi, the round off error and the exact solution. Let us call this as equation number 3. Okay. Fine. Okay. then let me do some algebra here. Let me subtract equation 2 from equation 3. Okay. So, that means 3 minus 2, what would this give rise to? By the way, are these equations linear? They are all linear, right, because we have, it is basically a linear algebraic equation for one cell is what we are looking at. So, can we subtract 3 minus 2, right? Okay. If we do 3 minus 2, what would you get? You would get an equation in terms of epsilon, okay. That will be what? A p times epsilon p equals, what will be on the right hand side? A east times epsilon E 0, right, and phi capital E 0 term goes away, plus A w epsilon w 0 plus A p naught minus A east minus A west times epsilon p 0. Is that correct? For every term there are 2 terms in the corresponding term in the other equation. So, essentially the phi, capital phi terms all go away and then only the epsilon terms remain. So, what have we got? We got an equation that governs the round off error, and the round off error apparently satisfies the same discrete equation as the original equation that we have. Okay. So, that is what we got. That means, the round off error satisfies the original equation, okay, as the solution, right, as the dependent variable. The round off error also satisfies the same equation. Okay. So far so good. Now, of course, we talked about this round off error epsilon. Okay. Now, we need to introduce a model for this round off error, right. So, we got some round off error which is basically a function of what? Both space as well as time, right. It is basically a function of both space and time. Space, we are for the moment considering it as only x direction, otherwise it will be x, y, z as well if we have a 3D system. Now, what is that we are actually looking for in terms of stability? We said a scheme would be stable if the round off errors decrease or do not decrease. They should not increase, right. That is the only condition. That means, the round off errors should not grow from time step to time step, right. So, if we consider a particular x and between 2 time steps, that is t and t plus delta t, what will be this ratio between the round off errors for these 2 time steps? So, we are looking at the ratio of round off error between in a time step, right. So, that will be epsilon x t plus delta t would be the round off error at time t 1, right, divided by epsilon x comma t would be the round off error at time level t naught, right. Now, what do we want this term to be? Less than or equal to 1. So, let us call this as amplification factor, okay, which is basically less than or equal to 1, such that the round off errors do not grow from time step to time step. Okay. So, that is what we are saying. Fine. But as of now, we do not know any form for this round off error. Okay. So, we can assume that the round off error is composed of several modes, right, as in a Fourier series, right. So, that means, I am introducing a model for my epsilon x of t is being composed of several waves, okay, that are basically as a function of space and time, okay, that will basically be and I am also assuming that it is in the form of an exponential function, okay, or is made up of cosines and sines. So, basically is a function of your trigonometric function. So, that means e to the power I k m x times e to the power lambda m t sigma m goes from 0 to some capital M or infinite. Okay. So, essentially I have introduced a model here for the round off error that we get in a computation. Okay. Now, I have assumed that this round off error is composed of several waves in space and in time, okay, and there are also functions of exponentials. Now, why should these functions be exponentials? That is a question to you. Why can't it be some polynomial, some x square, x cube or something like that, right? That is a question for you to ponder and come back to me, fine. And this k m is a wave number, okay, that is basically m pi by the length of the domain, right. If we take a length as L for the problem, this would be the number of waves that you can get, right. So, what we are saying is that these round off errors are composed of several waves, right. Each of these waves are defined by m, right. If you set m equal to 1, you get one round off error and you get another round off error and so on. That means, what we are essentially trying to say is, if I have a, let us say this is my domain L, right. If I have some epsilon, this is a round off error, I would say my round off error is something like this in the computer I am using. Okay. Now, what we are saying is, we are modeling this round off error using a set of cosines and sines, right, essentially using a Fourier expansion. Is that correct? Right. We have several waves and then we are modeling as a linear combination of all these several waves, and then we say we can somehow represent this using a linear combination of all of these things, right. And the round off errors also may grow in time or may decay in time, we do not know. For that matter, we have introduced this thing called e to the power lambda m t, where lambda m can again be either a real or an imaginary constant. Okay. Fine. Questions? Is it okay? Everybody okay with this? We have some random distribution of the round off error in a computer over the entire domain, and that distribution is what we are trying to approximate using several waves, right, with several modes, right, several frequencies that we have using the wave number k m. Okay. Fine. Everybody okay with that? Of course, the question remains is why it should be exponential. That is one thing which you have to kind of look at and come back. Okay. So far so good. That means, if I would substitute this model for the round off error, I can go back and look at what would be my values for this amplification factor, right. Essentially, I want to see the amplification factor for what? For this particular scheme, right. We have considered an explicit scheme. For this scheme, what will be the amplification factor is what we want to look at. In order to do that, because we want to solve for this, we have introduced a model for the round off error. Okay, that is all we have done. Now, what about the linearity of this equation? Is this equation linear or non-linear? The original equation, this one, discretized equation, this is a linear equation, and even if you have source terms, what would this equation be? This will always be linear, right, because you would somehow circumvent the non-linearity of the source terms or diffusion by introducing additional iterations, but the resulting equation we would solve would always be linear. Okay. So, this is linear. Now, what is the solution variable here? What are we solving for? Epsilon. Okay. We are solving for epsilon. Now, we said epsilon is composed of several modes, sigma m equals 0 to capital M. Now, because this equation is linear, we can use theory of linear superposition, right, because the solution is linear, it will be summation of all these solutions, right. I can use linear superposition theory because the equation is linear. So, the simplification we are trying to get out of this is basically, we do not have to look for each and every term of this error, right. We do not have to look for each and every little m, rather we can just look for one particular m, right, and if that is unstable, it will make the entire system unstable, right. As a result, I do not have to look for each and every wave here, rather I would look for just one component of the solution, okay, and that component happens to be just some arbitrary value. Okay. So, we are looking at some let us say some epsilon m of x comma t, this would be one particular mode. This is basically e to the power I k x e to the power lambda t. So, we say if this mode is unstable, if this particular solution is unstable, then the original equation will be unstable, because it is all linear, there is no non-linearity. If you have non-linearity, then things could probably get damped and there will be some interaction, right. As a result, because of the linearity of the original equation, we can look at the behavior of a single term in the expansion. Okay. Only one term is what we can look at. Fine, good. Then what will be now? What are the grid points we have? We have east, west, and P, right? Let us say P is characterized by x comma t. What would be the east cell? Will be x plus delta x comma t, and west would be x minus minus delta x comma t, and if it were at time level 1, you would also get in addition t plus delta t, right. These are all at value 0. If it were at 1, you would get at corresponding t plus delta t, right, all these things, correct. That is all we have. We have looked at the solution. Then if I go back and use the same equation, basically this equation, right, and substitute for the error in terms of the single mode that we have, right. So, what are the terms we have to now calculate? Epsilon p, epsilon east, west, and epsilon p all at 0, right, all these at 0. So, what will be epsilon p at time level 1? What will this be? E to the power I k, what will be the x value? X, what will be e to the power lambda t plus delta t, right. We are plugging in what is the p values for epsilon p. What will be epsilon west 0 or rather east 0? What will this be? E to the power I k x minus delta x times e to the power lambda, sorry, this is x plus, and then what about lambda t or t minus delta t or t, okay, t, okay. What about epsilon west 0? E to the power I k x minus delta x e to the power lambda t, right. So, essentially what we are doing is we have this particular mode, we are just plugging in what is this for each of the p east west and at time level 0 and 1, right, that is what we are doing. Yeah. All of these modes will satisfy. So, essentially your equation would become a equation in terms of a sigma, right. Can't you directly calculate what? No, but x is what varies over 0 to L. I think I did not get your question. So, we have a model for the error in terms of some exponential functions, and we are considering one particular mode of that, right, and with a hope we want to substitute this model that we have introduced into the original equation, right, and see if that error grows from time step to time step. That is what we are trying to do. We will get a value of at the next time step, yes. Sure, essentially that is nothing but you will get again in terms of e to the power lambda delta t, right. So, we do not know what is that lambda delta t. Now, that lambda is what we are interested in, right. So, we do not know lambda. Now, is there a lambda that will make it grow from time step to time step? That is where we have to bring in the governing equation. Okay. So, essentially the question is we said we have modeled the error using something, right. I said okay, I gave you a problem or you gave me a problem, and then we said okay, the error is basically some sin 2x is what we said. Now, sin 2x times e to the power t, I said. Of course, this will grow because you have e to the power t. If it were e power minus t, it would actually reduce. Now, the idea is can't we just substitute this back, or can't we just calculate what is e at delta t divided by e at t? We cannot, because that is where this constant e power lambda t is still remains, right. For that we have to put back this model that we have introduced for the solution back into the discrete equation for error, right. That is where the equation comes into play. Otherwise, your equation is disconnected from the model we have introduced, okay. But we have to make sure that this model we have introduced would not override all the things that we have in the equation, right. Fine, is that clear? Okay. Fine, we will come back to, actually we will use what you have suggested, it will come as a part of it. Okay. Now, so these are the values. Do we need to calculate anything else? Do we need anything else in the equation? Epsilon p is done, east 0 is done, west 0 is done, what else? Epsilon p 0 needs to be calculated. What is epsilon p 0? E to the power I k x times e to the power lambda t. Okay. Now, can we substitute all of these, okay, back into in equation, what equation number was that? Let us call it 4, okay. This is 4. So, substitute into equation 4. So, we have A p epsilon p equals A east epsilon 0 plus A west epsilon west 0 plus this coefficient times epsilon p 0. Okay. So, substitute into equation 4, what will be, what is that we get? A p times epsilon p is e to the power I k x e to the power lambda t plus delta t equals, on the right hand side what do we have? A east times epsilon is 0. So, this is e to the power I k x plus delta x times e to the power lambda t plus A west times e to the power I k x minus delta x e to the power lambda t plus what else? A p 0 minus A east minus A west times e to the power I k x e to the power lambda t. Okay. Now, what do we see? We see that e to the power I k x e to the power lambda t is common in all the terms. So, we can cancel it and also divide everything with A p on both sides. Okay. So, essentially divide using e to the power I k x e to the power lambda t times A p on both sides. Okay. So, if I do this, what will remain on the left hand side? E to the power lambda delta t equals, on the right hand side, A east upon A p times e to the power I k delta x. The next term would be A west upon A p times e to the power minus I k delta x plus A p 0 minus A east minus A west times upon A p times 1. Okay. That is all, right. So, that is the equation we get. All right. So, if we go back to our definition of what is the amplification factor, epsilon x comma t plus delta t by epsilon x comma t, right. This is for a particular mode, let us say sub m. So, if you substitute back into this equation e to the power I k x e to the power lambda t, what will this be? This will be e to the power I k x e to the power lambda t plus delta t upon e to the power I k x e to the power lambda t. So, how much is this value? E to the power lambda delta t. Now, what do we want? We want this guy to be, in a magnitude sense, we want this guy to be less than or equal to 1, right. Now, what have we obtained for this from the scheme? From the scheme, this value is nothing but everything on the right hand side, right. So, that means everything on the right hand side here, we want it to be less than or equal to 1 if we do not want our errors to grow from time step to time step, right. So, essentially we want this condition for what? Stability. Okay. So, the derivation is not finished yet. we will introduce the coefficients, which is gamma by delta x for A east, A west, and so on. We will plug this back into the e to the power lambda t expression and then simplify and see if we get a condition for the explicit scheme. Okay. So, we will do that in the next class, and you would verify the same thing for implicit and Crank-Nicolson schemes, and you would see that you will not have any condition on the stability. Okay. That is what you would do later on. Fine. So, we will pick it up in the next class, and thereafter we will move on to diffusion on unstructured meshes and so on. Fine. Okay. I am going to stop here. Thank you. See you in the next class.